Well, hello everybody. My name is Stephen Price from the Bristol Astronomical Society, and it's my pleasure to be chairing this evening's session. On behalf of the Bath, Bristol and Cardiff Astronomical Societies, I'd like to welcome you all to this beginner's course for astronomy and hope that you really enjoyed the topics we're going to cover this evening. This is the third session of a six-part programme, and this evening's theme is large-scale cosmos. But first of all, as ever, some quick guidance on attending this evening's session over Zoom. Please will everybody remain muted during the session so we can avoid any distractions to the speakers and the audience. We can mute attendees if required, and we really do appreciate your cooperation in this. If you have a question during or after a talk, then please type your question in the chat box on Zoom. We'll have a few minutes at the end of the talks to answer some of these questions, and we'll respond to other questions after the session is closed and let you know the answers. So that brings us to our two talks for this evening. Our first talk is entitled Cosmology, the Study of the Universe as a Whole by Dr. Jane Clark from the Cardiff Astronomical Society. A few words about Jane. Jane is a retired amateur astronomer and has a PhD in physics and an MBA from Warwick University. Jane became interested in both astronomy and photography as a teenager in the 1970s, photography much more seriously, although as her career progressed and family commitments increased, both interests lapsed. She acquired a telescope in 2006, shortly after completing her MBA, and quickly became hooked on observing. This experience made her realize that astronomy is a lot more fun than business administration. In 2017, she achieved her ambition of having an observatory in her backyard. Jane is a member of Bristol, Cardiff and Newtown Astronomical Societies and was a founder member of the West Norfolk Astronomy Society. Jane gives talks on astronomy to astronomical societies, schools, and other societies as diverse as the Cub Scouts, the University of the Third Age, and the Church's Wives groups. So, with no further ado, I'd like to invite Jane to talk to us on cosmology, the study of the universe as a whole. Over to you, Jane.
So, we're out in the entire universe at the moment, and really, the study of the universe as a whole, what are we studying? Well, that's changed over the centuries as our view has moved outwards. And I think the people who started cosmology in ancient Greece would be very surprised by what we've got as a view of the universe now. And if truth be told, I find the whole thing very surprising. And how did we get here? Anyway, how big is the universe? Well, the brief and simple answer is that we don't know. But you may have heard of a telescope out in space called the Hubble Space Telescope. It took a photograph called the Ultra Deep Field. Basically, they pointed it at the same part of space, a place where it was known that the view wasn't going to be cluttered by stars from our galaxy. And in this tiny region that they photographed, they exposed it for weeks and weeks and weeks and weeks. And they found 10,000 galaxies in this tiny region. Now, if you assume the universe is the same in all directions, which is a pretty reasonable assumption, then that implies that, we have the capability to observe 130 billion galaxies. And each of those galaxies, like the ones in the picture, contain about 100 billion stars. And each of those stars is 1,000,000 times the size of the Earth. So, we don't know how big it is, but we do know it's enormous. Now, the solar system, this was really discovered by 5 men, whose pictures are shown in the Rose Gallery there. And of those 5 men, it started really with Copernicus, and it took a quarter of a millennium to get to Newton, who really completed the discovery of the solar system. And I've categorized the people. Copernicus was a theorist. He never made any observations. He just didn't like the Greek theories and thought he could do better. Tycho, this gentleman here, was an observer. Galileo was an observer and an experimentalist. Kepler, who actually worked for Tycho at one stage, and after Tycho died suddenly, Kepler took over, was a theorist. Again, he actually invented a form of the telescope, but he wasn't really an observer. He was a mathematician. And Newton did experiments, but they weren't on mechanics in the solar system. They were mostly on optics or alchemy. So from this point of view, and of course he was one of the greatest mathematicians that ever lived. So he was mainly a theorist. Now these people, as they put together this picture of the solar system, which is pretty much our modern picture of the solar system, they had some idea that the sun was a star, like the stars they could see at night, but they couldn't measure stellar distances. I mean, this we're talking now in kind of Newton's time in the 1600s, early 1700s. And a contemporary of Newton's called Huygens estimated that Sirius was about half a light year away. It's actually about 8 light years away. So having discovered the solar system, they had some awareness that it was not the whole universe. And once telescopes were introduced, over time they gradually improved. So introducing them, which was done by people like Galileo, was a revolutionary step. But since then, development of telescopes has largely been evolutionary. And Herschel in the late 18th century, that's late 1700s, worked out the distribution of stars. So he got the first idea of the Milky Way shape. And Herschel, in fact, collaborated with his sister. And it was the Herschel siblings who did a lot of their work. And Caroline Herschel, the sister, during her lifetime held the world record for the number of comets discovered. So she was a substantial scientist in her own right. And was really the first female scientist celebrity. She was much sought after in upper class social circles. Now, the first person who accurately measured the distance to a star and got pretty much the answer we know now was this guy Bessel. Those of you, there may be one or two of you who've done science or engineering or maths degrees, and may have heard of Bessel in the context of mathematics, because he was also a substantial mathematician. But his contribution to astronomy was that he was the first person to succeed in measuring the distance to a star. He started out as an accountant, by the way, and like me, he found out that business administration wasn't where it's at. Now, we all pretty much know what a telescope is, I think. But there's another key tool which we'll come back to time and time again in the study of astronomy called spectroscopy. Now, this was a revolutionary change. It started with Newton, who did do a lot of optics experiments, and he discovered in 1672 that light splits into colors. Now, Herschel, that was the gentleman we mentioned earlier as having the first suggestion as to the general shape of our galaxy. He put thermometers next to the spectrum, and what he found was that, I mean, where the light fell, the thermometers showed a higher temperature, but where you couldn't see any light there, the thermometer still went up. So he discovered that not all light is visible. And Henry Wollaston discovered in 1802 that the solar spectrum, which goes from red, yellow, yes, all the way down to violet, that in fact there are discontinuities in it. These dark lines appear. So there was an interesting thing that meant there was more to a spectrum than meets the eyes. And from having discovered it, a guy called Fraunhofer developed a lot of knowledge of the solar spectrum in the early 1800s. And one of the things about spectra is that they're chemical tools. You can tell what atoms are present and molecules. And then there is a hydrogen spectrum with lines missing, so that's like the sun spectrum. But you also get what's called an emission spectrum. And you'll notice that these lines line up like that. So if you spot that pattern of lines, whether it's in an emission spectrum or an absorption spectrum, you can identify hydrogen. So that's chemical information. And there's the spectrum for hydrogen, helium, neon, sodium, and mercury. And I remember we had to do it when I was a physics undergraduate. We had to look at a sodium light, and I think I discovered about 18 lines that were visible. You can't see them all here, but they were there, and some of them were pretty faint. Now, it took 100 years, 120 years for people to understand why this happened. Well, Fraunhofer started the discovery of it, and Heisenberg, he of the uncertainty principle, actually worked in a spectroscopy department in his university, and he was the one who figured out why these spectral lines do what they do, and that was in 1925. Another trick you could do with spectra, I mean, this is really, you're beginning to get the idea, I hope, that spectra are pretty important, is you can use them as thermal tools. And the Victorians gradually discovered this, and it was finally solved by two people in Germany, Planck in 1900 and Einstein in 1905. And stars are classified by color and temperature. And the observational work to do this was mostly led from Harvard University. They had telescopes both in the Northern Hemisphere, we're talking the early 20th century now, and in the Southern Hemisphere. They did not let women use these telescopes, but they did let women analyze the photographs that were taken. And in fact, there were some very substantial discoveries made by these women. But the spectrum that you get, for instance, I mean, if you're not used to looking at graphs, that's the intensity in some units or other. But at 7,000 Kelvin, which is effectively 7,000 degrees centigrade, give or take a little bit, you get a peak there in the violet. And at this wavelength, you get some emission. Say at red, you get some, and so on down there. Now, if you're at 3,000 Kelvin, which you think of it as 3,000 degrees centigrade, you'll get, see, it's brightest in the red. And so at 3,000 Kelvin, if you see a star whose surface is at 3,000 Kelvin or 4,000, it'll be red-ish. You see a star whose surface temperature is 6,000 Kelvin, like the sun, it looks like that. And the sun looks kind of yellow to the eye. And at 7,000 Kelvin, it will look blue. So hot stars are bluer, cool stars are redder. That's the deal. Now, and in fact, helium was, the stuff they put in balloons to make them float, was first noticed in the sun spectrum before it was discovered on Earth. And it was discovered that the sun is mostly hydrogen. I mean, you may have heard this notorious story that Cecilia Payne-Kopochkin was a research student at Harvard University, discovered this, and her external examiner for her PhD was this guy, Russell, who said, no, that's not true. You've got to put some words in there to say that it looks like this, but it's not actually true. So she did. And then a few years later, Russell claimed he discovered it himself. So it's a bit of a blot on Russell's character. But anyway, this woman did. She went on to become the first female professor at Harvard University, so she didn't do so badly for herself. Now, Russell and this guy, Hertzsprung in Europe, discovered that if you plot brightness that way against temperature that way, stars don't randomly fill that graph. There is a sequence there like that, the main sequence, which is what they first discovered. And then there's a sequence there for giants, a sequence there for supergiants. Betelgeuse is a supergiant, and a sequence down there for a special type of star called a white dwarf. There's a companion around Sirius, which is a white dwarf. So this was really the key piece of observational evidence that people used to work out the theory of stellar evolution. The first thing they had to discover was, because nobody could understand why stars would stay so hot for so long, before Eddington pointed out in the 1920s that it was nuclear fuel. Bear in mind, the atomic nucleus had not been discovered till 1910 by Rutherford, or thereabouts. Stellar structure, the first person to work on it was Emden, but in the 1920s, Eddington is the name most associated with it. He was at Cambridge University. Meanwhile, back at the nebulas in the sky, nebula is a term you'll hear in astronomy. Nebula is Latin for cloud. And telescopes were finding nebular objects. So there's a 19th century telescope owned by a guy called Lord Rosse, who was a sort of, a Victorian industrialist who made a pile of money. And some of these nebulae that they were finding with telescopes, gradually over the years, people began to identify spiral nebulae as a subtype of these. And I mean, these early ones are definitely drawings or paintings. These later ones are photographs. And photography greatly accelerated this work. And this is an early photograph from 1888 of the Great Nebula in Andromeda. So where we now, people, by about 1900, telescopes could resolve faraway stars as well as nearby ones. Of course, you can just look up and see nearby ones. Henrietta Leavitt in 1912 found a way to measure the distance to a small southern hemisphere nebula, which we now know to be a galaxy, called the Small Magellanic Cloud. And she used a type of variable star, which people were beginning to realize existed, called Cepheid variables. And if you plotted the magnitude, see, the 0 magnitude is bright, 25th magnitude is unbelievably dim. And for the sorry, it says LMC, it should say Small Magellanic Cloud. That was Leavitt's law for the Small Magellanic Cloud, that the period over which it varied in days was directly related to the brightness. Hubble later recognized some Cepheid variables in the Andromeda Nebula, and his plot of those, I mean, this was well within what people could observe then, so it's a fairly accurate looking straight line there. Hubble was absolutely at the limit of what people could observe in his day, and he was using what was then the biggest telescope in the world. So his data were kind of, less obviously linear, but they were still pretty obviously linear. And the brightness of these was 5 magnitudes less bright than that. So if you do the maths on that, it turns out that means that the Andromeda Nebula must be 10 times as far away as the Small Magellanic Cloud. And it therefore was clearly outside our galaxy. So the idea that there are more than our galaxy is just one of many galaxies was born. And now the universe is seen to be made up of galaxies, not just planets and stars. Now, spectroscopy's next trick it had up its sleeve was that movement away from us stretches waves. See, if you've got an object moving that way there, these waves get stretched, and these waves get compressed. And red wavelength has a longer wavelength than red light, has a longer wavelength than blue light. So if your spectral lines are shifted to the red, that implies you're moving away. If you don't understand that, don't worry, just accept it. That redshift means moving away, and blue shifted means moving towards. So in the direction in which you are looking, not sideways, but in the direction in which you are looking, spectroscopy gives you speed information. Now, the galaxies, it turns out, are redshifted. And there was a guy called Vesto Slipher in the 1910s who noticed that, but just noticed it as a fact. And the further the galaxies are away, because Hubble had a method of measuring the distance to these galaxies. Now, the further away the galaxies are, the greater the redshift. So this was the plot that Hubble came out with, showing that the further away a galaxy is, the faster it's moving away from us. In other words, the universe is expanding. So not only have we now had this time of very great change in the 1920s, where it was discovered that the universe consisted of galaxies, but we also found that these galaxies are moving away from one another. So it's an expanding universe of galaxies. And this expansion has since been confirmed by many, many observations. And the argument runs, well, if they're expanding like that, redshift is a proxy for how far away they are, then what happens if you wind the clock back? If you wind back the movie, all the galaxies must have been in the same place about 14 billion years ago. Billion is 1,000 billion, you're not sure. So it seems that there was an event of some kind in which they all flew apart. But actually, it's not the galaxies that are moving. What's happening is that space is expanding. And space was created in this event when it was all together. And it's still being created as these galaxies move apart or appear to recede from one another. In other words, the Big Bang didn't explode into anything. Space exploded and took the Big Bang with it, which is kind of a difficult concept to wrap your head around, I know. I've struggled with that one for a long time. So the evidence for the Big Bang. The galaxies are getting further apart. The rendering is seen in spectra. We've done that. And light is stretched as space expands. So that's what we've just discussed. Also, there's an echo in cosmic microwave radiation. The reason is complicated. The alternative to the Big Bang was a steady state theory, which was proposed in the 1940s. And that doesn't predict the cosmic microwave background radiation. So while that theory was taken seriously before the microwave background radiation was found, and the microwave background radiation was predicted about the same time by these guys. But in the 1960s, these two people, they were working for the American Bell Telephone Company. And of course, they were interested at that time in radio communications to extend our telecommunication range and satellite communications and stuff. So from an engineering point of view, they had to work out what all the noise was in the radio signal and get rid of it. And quite by accident, they found this background radiation and got a Nobel Prize for it because they spoke about it to the astronomers at the local university. And they said, well, have you read this paper by Galmov and company? Now, another prediction that the Big Bang makes, again, don't worry if you don't understand why. It's all complicated stuff. But it predicts that there's about 24% of the universe. The universe is the vast majority of it is hydrogen and helium. It predicts 24% is helium. We observed 25%. So that was also a big nail in the coffin of the steady state theory. Because the steady state theory required a universe hundreds and hundreds of billion years old to make the helium in stars. But we just don't see any evidence of this. The universe has aged and matured quite detectably in the last 14 billion years. An example of that is a phenomenon called quasars. Don't worry if you don't know what they are. But they were found, there are no quasars near us. They're all a very, very long way away, and they're all very, very bright. So, since when we look back, because light has a speed, we look back in time, that's an example of evidence that the universe has matured. And the galaxies that we see far away at earlier times were noticeably different from today's galaxies. So by now, the evidence for this Big Bang is just overwhelming. But we don't know everything. I mean, we are still on a journey through cosmology to discover what's going on in the universe, and we are by no means there yet. First puzzle is a puzzle of missing mass. Galaxies are known to cluster together, and you saw that a little bit if you had your eyes open in that sequence of galaxies with that rather lovely music at the beginning. And we can measure how it, and what you can do is when you've got a cluster of galaxies in the radial direction to and from us, you can measure how fast they're collapsing. We can't really measure the sideways collapse speed, but we can measure the front and back collapse speed. And if there's a big cluster of galaxies, that's enough to tell how fast they're collapsing under gravity. And these galaxies, you use, I mean, the most up-to-date theory of gravity we got is Einstein's theory. And we use that, and, you know, according to that, we need more mass to make these galaxies collapse that fast. So there are two possibilities. One is there is some dark matter that we can't see. And the second possibility is that on a scale of cluster of galaxies, our gravity theory is wrong. Because the gravity theory, well, first, Newton developed it for the solar system. Einstein developed it a bit further, but on scales much greater than the solar system, Einstein's theory has been shown to be more accurate than Newton's. But it might be that actually we still haven't found the ultimate theory of gravity yet. And I would say probably 90%, maybe more, of professional cosmologists work on dark matter, and about the rest of them, which is a much smaller number, work on modifying gravity. And there's been a huge amount of effort because the presence of a rival theory means that the dark matter people have had to work a bit harder to prove they're right, as it were, or to show they're right. So these guys have acted as devil's advocate. But the thing is that there has been no observation yet which knocks one or other of these theories out. So we still don't know. And we have no clue what dark matter is. You know, I mean, the particle physicists are a bit like cosmologists. You know, they're often wrong, but they're never modest. And they think they know everything. Well, they told us we were going to discover it with this Large Hadron Collider at CERN in Switzerland. Well, they haven't. So, you know, the properties of dark matter, people are beginning to have to make them look more and more magical to make the theory of dark matter hold up. So there's a big question mark there. We don't know.
Jane, 1 minute.
I've got 2 slides.
Okay, 1 minute to go. Thank you.
Thank you. The second puzzle is star formation. We know that galaxies make stars, and we know that a whole galaxy is needed to make a star-forming nebula of gas. You can't just form a nebula in the middle of nowhere. But we don't yet have a theory of that. And there are hundreds of professional astronomers through the world working on this. And the third puzzle is the expanding universe. The expansion is getting faster. We don't know why. Is it repulsive gravity at long distances? And when Einstein put his theory of gravity together, he did show that you could have a repulsive term that solved his equations. But he was very come-see, come-sa about whether that was physically real. And the allegation is that dark energy is the repulsive term in Einstein's theory. Now, this theory is out by a factor of 10 to the power of 120. That's what 10 to the 120 is. It's 1 with 120 zeros after it. So it is a huge number. And if your theory needs to be multiplied by that huge number to get it to work, it's wrong. Very wrong. The most wrong theory in history. And with that, I'll leave you.
Well, thank you very much, Jane, for an excellent introduction to cosmology. Really was life, the universe, and everything in that talk. So that was really good. And please feel free to give virtual applause to Jane for an excellent talk. Thank you, Jane. There will be a bit of time at the end of the session for some questions or any questions for Jane. But we'll move on, first of all, to our second talk for this evening, please. And the title of that talk is Nebulae, Star Clusters and Galaxies. And that's going to be given by Dr. John Henn from the Bristol Astronomical Society. Now, a few words about John. When John was a boy, he always wanted to build flying saucers and launch them from Peru. and he was inspired by the radio series Journey into Space. In 1971, as a member of the Hawker-Siddeley Dynamics team, John watched Europa 2 being launched from Kourou in French Guiana, the north coast of South America. The first stage was Blue Streak, which worked perfectly. However, the Italians were proud that their satellite was still sending signals when it hit the ocean. John has a degree in physics from Warwick and a PhD in magnetic suspension from Sussex. He's worked at Filton on various space and defence projects and later produced online learning software. John says, being a dreamer, I like to try the impossible. So I got involved in 1984 with trying to restore the 70-mile-long, very derelict Wiltshire and Berkshire Canal, and he's still very much involved in that today. John was brought back to astronomy by evening classes with Dr. Rodney Hillier and joined the Bristol Astronomical Society a few years ago, becoming a committee member, and in John's own words, has been causing problems ever since. Well, I wouldn't agree with that, John, but I would agree to listening to your talk now, please. So, John, nebulae, star clusters and galaxies, and over to you, please.
So that's the Milky Way seen over Stonehenge. The same scene would have been seen for thousands of years. So when our ancestors and ourselves look into the sky, you're not only looking at a pretty scene, you're looking at a history. The reason for that is that light is traveling from those stars at 180,000 miles per second. So it's a finite number, or 300,000 kilometers per second. Why is that not? Okay. Right. So what we're going to do is look at how we measure distances. The distance between the Earth and the Sun varies between 152 million kilometers and 147 million kilometers. So the average distance is of 150 million kilometers, or 93 million miles. And for those who know a little bit of astronomy, that this distance between the Earth, the average distance between the Earth and the Sun, is 1 astronomical unit. Now, light takes about 8 minutes to cover the distance between the Earth and the Sun. Thus, 8 light minutes is equivalent to a distance of 150 kilometers, or 93 million miles. So, as Jane was saying, space is big, enormous. So we don't use kilometers or miles to measure the distance. We use light years. And a light year is something like 9 trillion kilometers, or 6 trillion miles. So you can see there that's a very important way to measure distances. So now we're going to look at nebula. We're going to look at star clusters and galaxies. So we start off with something we can see as faint patches in the sky, and nebula. So space is large and very, it's almost like a vacuum, but it's not a vacuum. It consists of low density gas, which is mainly hydrogen and helium, some dust, and radiation. So that's in space. Nebula are slightly more dense clouds. So a cloud, a nebula cloud the size of Earth would still only weigh a few kilograms. So this is huge. So you can see there's not much material in space, even in nebula. So how come, why do nebula form? That is because you get clumping of the material, gravity of a small clump attracts material to a bigger clump, etc. Or you could have a shock wave from a dying star, from an explosion of a dying star. That could bunch the material up. Now, many nebula are strongly related to the life cycles of stars. So this is the Crab Nebula, and it's associated with the death of a large star. So a large star here I think it was observed by the Chinese in the mid-11th century. And it's a massive star, 15, 20 times plus the size of our sun. And the result of this explosion is a tiny neutron star in the middle of that. And in this case, this neutron star is rotating very fast and becomes a pulsar. So this is the death of a large star. Death of a smaller star, like our sun, it will end up as a white dwarf. And in this case, sometimes these stars, they puff out a lot of material during the sort of dying stages. So I think it's something like 90% of stars in the galaxy will end up eventually as a white dwarf. So that's the death stars, or the death of stars for the nebula. Now we're looking at the birth of stars. And if you recognize this is the Orion constellation on its side. And in the Orion constellation, there is a molecular cloud, a huge cloud of gas and dust. Obviously, again, it's very diffuse, but within this cloud, you've got various nebula, the Orion Nebula here, and the Horsehead Nebula here, and the Flame Nebula. So they're all within the cloud. So the Orion Nebula, M42, is about 1,300 light years from Earth. It's 24 light years across and has a mass of 2,000 suns. It's an emission nebula because there is light from stars within the nebula, keeping it bright. And if you look very closely there's 4 very bright stars known as the trapezium, and that's powering the light in the nebula. The next is the Horsehead Nebula, which is an absorption nebula. That means there's dust in there, which blocks the light from behind it. So this nebula is about 14 to 1,500 light years from Earth, still part of that huge molecular cloud. And what you can also see here is another red emission nebula, the Flame Nebula, and then the Blue Reflection Nebula. So reflection nebulas sort of reflect light from nearby stars. So that's a very brief introduction to different types of nebula. And it's a great big topic in its own right. So from nebula, we started off with the death of stars, and the nebula we've just seen are the birth of stars. And these stars, they are part of a nebula, and then they form from the same nebula, they form stars. So they form open clusters of stars, which contain dozens or hundreds of stars, and they're often rich in gas between the stars. We know there are about 1,000 irregular clusters in our galaxy, and that we can view, and probably there are a lot more because they're the other side of the nucleus of the galaxy. So this is an open cluster, the Pleiades, or Seven Sisters, and we can see that with the naked eye. It's about 400 light years away, 86 light years in diameter, contains 1,000 stars dominated by a number of hot blue and extremely luminous stars. So that's quite a good constellation to look at in the night sky. So we've had the open clusters, which are sort of new stars being formed. And then we've got the globular clusters, and they're spherical collections of hundreds or hundreds of thousands of stars. They're nearly free from gas and dust and contain some of the oldest stars in the galaxy. And this is a picture of the Omega Centauri cluster, located about 16,000 light years away, most massive cluster, globally a cluster in our galaxy, containing several million stars. Now, it is believed, and this is from the telescope Gaia, that this was actually the nucleus of a dwarf galaxy which has been subsumed into the Milky Way. And at the center of that is probably a massive or reasonably massive black hole. So now, that's those clusters of stars. Now we go and look at the Milky Way as a whole. So the Milky Way galaxy consists of a disk of about 100,000 light years in diameter, a galactic bulge, a halo of stars, and you'll notice within the disk there are open clusters, and you'll also notice that the sun is approximately 26,000 light years from the center. So the number of stars in the Milky Way is somewhere between 100 and 400 billion, and the mass is about 800 to 1,500 billion times the mass of our sun. So it's quite big. So the disk, as I said, is a diameter of 100,000 light years, and it's got a thickness of about 1,300 light years. So the thickness of the actual disk is about 1,300 to 1,600 light years. What's interesting, it contains most of the galaxy's interstellar star-forming material. So again, if you look at it again, this star-forming material is mainly concentrated on the plane of the disk. So the disk rotates, and half the interstellar material is within 80 light years of the central plane. So you've got 80 light years there, very small, and then you've got 13,000 for the bulge and 1,300 for the disk. So it's concentrated in quite a relatively small area, or volume rather, I should say. So again, star formation does not occur randomly, but in spiral arms. So this is the rotation of the galaxies going around there. So due to rotation, there's an outward force, and in the center, there's an inward force. And obviously, because the stars are sort of kept in more or less the same position, then the forces balance. And our galaxy takes approximately 220 million years to do one rotation. So that's the disk. Now we go to the halo, which is a thin distribution of stars and globular clusters. It's spherical in shape, about the galactic center or nucleus, and the radius is about 65,000 light years. So it's big. So at the center of the halo is the bulge. So it's got its greatest concentration of stars are in the bulge, and the bulge is centered around the nucleus. So the bulge is about 20,000 light years long and approximately 13,000 light years thick. Now, what we'll be showing you at the moment, but this is effectively a bar in the center of our galaxy, and the length to the width of the bar is approximately 3:1. And we'll come across different types of spiral galaxies in a minute. So that's the bulge. And then at the center of the bulge is the nucleus, right in the middle. And if you look at the distances, we've got thousands of light years, but the nucleus is only about 400 light years from the center. So it's a very small part of the Milky Way. So it's now this is I thought this is an amazing fact, densest distribution of stars. So if you look at the concentration of stars where we are in the disk. We have, if you make a sphere of about 3.3 light years in diameter. So as you can see, there's one star. So when we look at our location, the nearest star, Proxima Centauri, is about 4 light years away. So in that space that would between us and Proxima Centauri, if we take that as a whole volume, we've got one star. In the nucleus, there are 50,000 stars in the same volume, which is, I think, it's an incredible thing. Obviously, if you've got a planet, there'll be no night. It's a region of violent and energetic activity. You've got the stars giving off radiation. You then possibly get collisions of stars and possibly the odd supernova. So life, I don't think, if Earth was stuck in the middle of our galaxy, I don't think life would have existed or would exist on that. So that's the core and the stars. And we've been looking at the center of our galaxy for quite a few years, and this is an infrared view, and we've been looking at these S stars over the last 10 to 15 years. And S2 moves in an orbit of about 1 light week in a period of 16 years. And its closest approach to this point here is 17 light hours, or 120 astronomical units. So 120 astronomical units is 4 times the distance of, so Pluto is approximately 30 astronomical units from our sun. So it's 4 times that distance, the closest approach. And radiation regions plus orbital speed details of this star and other stars, very close stars, there's stars that come even closer to the Sagittarius A. So the calculations reckon that Sagittarius A has a solar mass of about has a mass of 4.3 million solar masses. So it is good to assume that Sagittarius A is a massive black hole at the center of our nucleus. Center of our galaxy, at the nucleus or core. So that's the Milky Way galaxy. Now, Jane mentioned the Andromeda Nebula. And what's amazing, that 100 years ago, people didn't know whether these nebula were part of the Milky Way or not. Were they other separate island universes of star? And of course, Mr. Hubble, using the Cepheid variables, measured the distance and said, well, the Andromeda galaxy is far beyond the Milky Way galaxy. So on his CV, you could say he discovered the universe. So that's quite a good CV point to put on your CV. Right, so we're now looking at galaxies beyond the Milky Way. So we've got spiral galaxies, which are the most common. They're yellow in the middle because of the bulge and blue towards the outer edges. And the categorization depends on the spirals, how close the spirals are and how many there are. The barred spirals, as I said, the Milky Way is one. And again, it's the same sort of categorization. And apparently 2/3 of the spiral galaxies have bars. So this is just a picture of the pinwheel galaxy without a bar. The diameter of 170,000 light years and 27 million light years from Earth. Quite close, really. And then you've got this barred spiral, the Great Barred Spiral. So that's over 200,000 light years across, and it's 56 million light years from Earth. So it's, when you look up in the sky, there are amazing sights. So we now go from spiral galaxies to elliptical galaxies. They are yellow and rather featureless. They normally are in galactic clusters or smaller compact groups, contain older stars. Some are low mass, some are high mass. They lack star-making gas, but they have dust clouds. So here is famous M87, 53 million light years ago. It's in the cluster Virgo, home to several trillion stars. So it's big. It's a big galaxy, has a supermassive black hole, which, if you remember, the Event Horizon telescopes actually got an image of it. It's got 15,000 globular clusters. So the Milky Way is 150. Forgot to mention the Andromeda's got about 400. And it's a diameter of about 120,000 light years. It's a big galaxy, this one. So you've got the spiral and elliptical. Now you've got irregulars, which don't have a spiral elliptical shape. This is an image of a dwarf irregular galaxy. So some of these odd-shaped galaxies, these irregular galaxies, are a result from the interaction of galaxies. So in this case, two spiral galaxies have collided and have formed an irregular galaxy known as the mice, because of the long tails coming off the main galaxy bodies. So that's irregular galaxies. They can be large or small. The most abundant type of galaxy in the universe are dwarf galaxies, but they're hard to detect, the low luminosity, low mass, and small size. Most are elliptical or irregular, but there are some dwarf spirals. So diameter 300 light years to 30,000 light years. You know, the Milky Way is 100,000 light years. 10 million to 10 billion solar masses-ish. These dwarf galaxies most commonly found in clusters, often as accompanies to larger galaxies. So this is Andromeda with some dwarf galaxies around it. So galaxies, the universe got a hierarchical structure. So stars are not clumped randomly throughout the universe, but are clumped together into galaxies. Galaxies are clumped together into clusters, and clusters are clumped together into superclusters. Brilliant, isn't it? So our local cluster, the local group, contains 3 large galaxies and more than 20 dwarf galaxies. They haven't found them all yet. This is a photograph of the Magellanic clouds, that's large and small, which are irregular dwarf galaxies and can be viewed with the naked eye from the southern hemisphere. So they're part of the local group. So the local group has got these dwarf galaxies and then 3 major ones: the Milky Way, the Andromeda, and the Triangulum galaxy. And you'll notice the Triangulum galaxy is significantly smaller than our other two galaxies. So those are the main galaxies in the local group. So we've got quite a small cluster of galaxies, but if you look at the Virgo cluster, which includes the M87, it's approximately 50 million light years away and 10 million light years in diameter, and it contains over 2,000 galaxies. Then you go to the Coma cluster, which is 300 million light years away, 16 million light years in diameter, and it contains about 10,000 galaxies. So you're getting a bigger cluster there. Superclusters, and the biggest superclusters are 320 million light years or more long or in diameter, and they contain loads of sun. The mass is a huge amount more than the mass of the sun. So our local group and the Virgo cluster are part of the Laniakea supercluster, which is about 160 million light years in diameter. And that little red dot is the Milky Way. So it's amazing. It's the way the universe is structured. So we've now talked about nebula, star clusters, galaxies, galaxy clusters, and now we go to dark matter. And I'm just going to introduce this very quickly. So 80 years ago, Fritz Zwicky observed galaxies in the Coma cluster were moving so quickly that they should have been flung away into space. So this is a video of it, an animation. The stars in the cluster provided only 1% of the mass needed to keep the galaxies from escaping the cluster's gravitational pull. Only 1% of the matter you could see. The dark matter, there's only 1% of the mass needed to keep the clusters together. And Vera, in the 70s, Vera Rubin discovered the same type of problem in the individual spiral galaxies. The stars at the outer rim of the galaxy should have been flung out into space, but they weren't. So there was something there that we couldn't see, but added gravity.
2 minutes, please, John.
Right. So we cannot see. We cannot see it. Doesn't interact with atomic particles, etc. So how do we know it exists? Because of gravity. So Einstein sort of put the space-time fabric sort of bends. And if you look at galaxies, they bend the space-time around it. So light passing close to it is bent around the galaxy, producing an intensified multiple images of background sources. Strong gravitational lensing, and it turns the galaxies into huge natural telescopes. Again, visible matter is not enough to create the observed warping effects. So dark matter provides surplus gravity. And this is a picture of the Abell 370 galaxy. So there's mysterious blue streaks, which are actually distorted images of remote galaxies. It also has various multiple images. And in there, that is a galaxy which has been spread. So this is the lensing effect of dark matter, and most of it's dark matter. So dark energy, 69%. So this is the composition of the universe. Dark energy, 69%, dark matter, 26%, ordinary matter, 4.5%, of which only 0.5% is in the form of stars. Thank you for watching. So we've gone through nebula, star clusters, and galaxies. There we go. Thank you very much.
Well, that's great, John. Thank you for excellent talk on an introduction to nebula, star clusters, and galaxies, and some really fantastic images there you've shown in your slides. So appreciate that very much. So we're just up to the hour now, and before we go into any Q&As, some virtual applause for John for that excellent talk. Thank you, John. We're just going to go on for just a small number of minutes now to look at a couple of questions that have been asked. If you need to go now, feel free to do so, but this will only take a few minutes. We've had a couple of questions come in, I think, for you, Jane, if that's okay. The first one is from Alison Larner. How do we know what shape the Milky Way is?
Well, that's a very good question, actually. What I didn't mention was that there's been a tremendous amount of effort. It started in about the year 1900. There was a Dutch school of astronomers who were beginning to figure out methods of working. Well, people were learning how to measure distances to stars. I think that was the key thing. And so people began to get an idea of the size and shape of it from that. It's still ongoing. The real problem is that we can't see the center of our galaxy because of all the dust. Let me try and find you a picture. Give me a minute and I'll show you. Right, file. Open. Right, here we go. I'm just going to put the picture here. So on. Yeah, here it is. Right, I'll just, right, let's find the zoom window again. Actually, what I'll do is I'll slideshow current slide and then display settings, swap presenter view slideshow. Sorry, this always takes a minute. And now find the zoom window again and hit the share screen button. Oh, that's the one I want. Share. So you should now be able to see a picture of 3 galaxies. Can you see that?
Yeah.
Yeah, right. That one there is edge on. So you can't see the middle. And if I go back a slide, that's right. Yeah, there we are. I've blown it up in this picture. Yeah, you can't see the middle of that because of dust. We have exactly the same problem with the Milky Way. Because we are in that plane, we can't see the middle. And we can't see, you see the dust extends over most of the galaxy. So we can't see through that. We are beginning to learn how to see through it, in particular by using spaceborne telescopes and spectrometers to look in wavelengths longer than visible light, infrared in particular, because visible light is not transparent to dust. Infrared is transparent. So people are able to do things like measure distances to stars and measure angles to stars and so on. So the picture is still being put together today, but that's roughly the answer.
Great. Thanks very much, Jay. Thanks for those images too. Now, John's talk prompted so much deep thought that it took for your talk to finish before the questions came in, John. But I think you can have a sigh of relief. They're not asking you what is dark matter, so you're okay. So
That's good.
The first question is from Joe. Why do most spiral galaxies only have 2 arms?
I'm not sure. I think you've got a great variation of spiral galaxies. I mean, I showed you the picture of the pinwheel has got quite a few arms. So I'm not quite sure what causes. Do you know, Jana, what causes the difference in arms, the number of arms? But you've got the whole range. You don't only have to.
It's each galaxy tends to be surrounded. Each big galaxy tends to be surrounded by several dwarf galaxies, as John mentioned. And perturbations from those dwarf galaxies tend to be what enhances the spirals. The spirals themselves are not consisting of stars that move like that. They're waves that run through the stars. And I think the most common pattern that forms from these disturbances is a pair of spirals. You do get galaxies with more than 2 spirals, but they are, as the questioner quite rightly asks, they are rare.
Great.
Okay.
Thank you for that. And we've had one final question come in that we haven't answered yet, and that is also for John. What decides if a star should become a white dwarf or a black hole? And that's from Lee.
So it's just the mass of the star. So mass of stars 8 to 10 times the mass of our sun, likely to go through a supernova explosion. And at the end of that supernova explosion is either a neutron star or a black hole. Stars that are like our sun, perhaps up to a couple of times the mass of our sun, gently fade away. Well, they don't quite gently fade away. They have a different end of life, and they don't have a supernova explosion. They just sort of puff out bits of gas and end up as a white dwarf So it's it's just basically the mass of the star.
Yeah,
Right.
there have in fact been a few stars, very few, that are much bigger than that, like 30 to 50 times. And one or two have now been observed in our galaxy to collapse directly into
The black holes.
black holes
Yeah.
without an explosion.
Yeah,
They
because
just implode.
the biggest star that we know of is in the Magellan Cloud, and it started off at something like 320 times the mass of our sun. But these massive stars don't last very long, and it's only a couple of million years old. So its life
Yeah,
cycle.
they live fast and die young. And
Yeah.
that one probably is because the problem is the stars chuck stuff out. You know, the solar wind
Yeah.
comes out from ours, and you get these coronal mass ejections and stuff. And there comes a point where it chucks out mass faster than gravity can pull it in. That's what limits the size of stars. And this 300 solar mass one that John mentioned was a kind of rude surprise to the proponents of that theory, because according to that theory, it shouldn't be able to collapse that much. And so the suggestion is that it's probably because it's in a dense cluster of stars, that some stars have merged to form it.
Yeah. So the thing about astronomy, the more you go and investigate, the more you want to find out.
That is very true. And thank you very much, both of you, for answering that question.
Yeah.
We're about out of time now, so I'd like to thank you all for listening and for those excellent questions that have been asked this evening. Thanks very much. And of course, thank you for our two excellent talks tonight from Jane Clark and John Henn. So just want to look ahead now to next week. Our fourth session will be held on Tuesday, the 5th of March, again over Zoom, again at 7:15 for 7:30 start. And the theme next week will be space exploration. And an invitation will be sent out very soon to you all. So look forward to seeing you all then, and goodbye for now. Bye-bye.